So today's lesson is implicit differentiation. And we want to start off with a nice basic example. And so what we have to remember here is if we're asked to derive a function that's given implicitly, that means there's going to be some x's and y's, or basically the independent and the dependent variables within the problem. And it's not going to be ideal, so we're going to have to kind of approach this a different way. So as we've been doing, the derivative of any term with respect to x is basically just applying regular rules. So the derivative of x cubed would be 3x squared. Now what we've never really written in the past is that we just did the derivative of x with respect to x. And the reason we don't write that is because in essence it cancels itself out. But where that becomes important is when we go to derive the next term, and that would be the derivative of a function involving y. So that would be 3y squared, but that would be the derivative of y with respect to x. And so that gives rise to that expression dy dx. So as we're solving for the derivative, up pops our derivative notation. Now we also have to remember to derive both sides of the equation. So in this case, it's nice and simple. There was already a 0 there. But just for argument's sake, let's suppose that that was 100. Well, the derivative of 100 would be 0. If, let's say, this was 100x, then the derivative of that would be just 100. So we do have to remember to derive both sides. So that would make us equal 0 here. So the first step is the calculus, and then from there on in, it really just becomes algebra. So we're going to have to solve this for dy dx. So all we want to do is isolate dy dx. So 3y squared times dy dx would equal negative 3x squared. Finish off, dy dx would just equal negative x squared over y squared. Now let's look at an extension of this. What if we were asked to find the second derivative of this expression? So let's go to the next page here. What do we know? We know that dy dx equals, if we remember it from the previous page, negative x squared over y squared. And we have a couple choices here. We can either approach this using the quotient rule, or we can bring that y squared up and we can use the product rule, which is, I think, where I'm going to go here. So let's rewrite this as negative x squared times y to the negative second. So to get our second derivative, that notation would be d2y over dx to the 2, right? So the second derivative of y with respect to x. So we're going to execute the product rule. The derivative of the first term is negative 2x, but that's times y to the negative second, plus we have negative x squared, and now we have the derivative of another term involving y. So that's where we have to write negative 2y to the negative 3 times dy dx. Now at this point you're pretty much done, except the issue here is we can't leave our expression like that because we have a dy dx here. So this is always a mystery for a lot of students. They don't really understand how to kind of simplify this. And the reality is the answer to where we need to go from here is kind of hiding in plain view in front of us. It's this we need to get out of the problem. And we have dy dx. We actually just found it in an earlier step. So we can do that, or we can do our product expression. But either one of those would flow in there. So let's see what this looks like. So we have negative 2x y to the negative second. That doesn't really change. Here we have a, right now, positive expression, x squared times 2y to the negative third times dy dx. So let's call that x squared, negative x squared, y to the negative second. So when all is said and done, our second derivative here would be negative 2x y to the negative second minus, because of that negative here, see a 2. And then we're just going to apply properties of exponents here. So it looks like x to the fourth, y to the negative fifth. Now, of course, there's always some things you can look to do. In a case like this, you might think about taking out a 2. You might think about taking out an x to the first, a y to the negative fifth. And those are all things that could be done. But I just think for simplicity's sake and for what we're trying to do here, we're going to leave our answer like that. Okay, let's look at maybe just a little bit more of a complex problem, something where we have to look out for the product rule or the chain rule, and this is a great example. So again, I kept it simple on the right side. We'll just leave that as 0 for now. And so if we're trying to find dy dx, we have to find the derivative of a product, or I'm sorry, of a function who has a differentiable function inside of it. So let's go execute the chain rule here. Secant squared of xy times, and here's the chain rule piece, the derivative of xy. That's a product. So we have to say x times the derivative of y, which is 1. But since we're taking the derivative of y, we have to put dy dx. Plus, now we switch it up, right? Y times the derivative of x. And of course, that would all equal 0. So at this point, the question is, what do I do? And I think what I might do in this case is I think maybe we'll go ahead and distribute. So that would be x secant squared of xy dy dx plus y secant squared of xy, and that equals 0. And as before, now comes the algebra, right? Now we're trying to solve for this right here, dy dx. So we're going to slide that over, right? So x secant squared of xy dy dx equals negative y secant squared of xy. And lo and behold, what happens here when we divide out on both sides? We see that the secant squareds are going to cross out, so our final derivative here is just negative y over x. Now, you might be thinking to yourself, well, did I have to distribute? And the answer really is no. If you had divided right off the bat by secant squared of xy, obviously 0 divided by that would just be 0. And then you have a much simpler expression right away to solve for dy dx. But of course, you would still wind up with the same thing. Okay, finally, let's take a look at how we can extend some of the things we've talked about in the past. So we can still write equations of tangent lines even though we have implicitly defined functions. So let's finish with this one. They're asking us to find the slope of a tangent line to this equation at the point 864. So the slope really is code word for us having to find the value of the derivative. At 864. So let's actually do something here. Let's rewrite this expression as x to the 2/3 minus y to the 1/3 before we go derive that. So here we go. I have 2/3 x to the negative 1/3 minus 1/3 y to the negative 2/3 dy dx, and that equals 0. Now, here's something to think about. I can solve for dy dx here, but I know that in this problem I have to plug in the 8 for x and the 64 for y. So I could do that right away, and I think that's what I'm going to do here. One thing I might do, though, is I'm going to rewrite this so it's a little neater to actually plug some stuff in. So I have 3 times the cube root of x on the bottom there, and I have 1 times 3 cube root of y squared times dy dx here. So let's go ahead and plug in. So if I plug in an 8 here, right, the cube root of 8 is 2. 2 times 3 is 6. So 2 over 6 is 1/3. Now here, the cube root of 64 squared. So let's do the cube root of 64 first. That's 4. 4 squared is 16, and 16 times 3 is 48. So now if I want to go solve for dy dx, it actually is pretty simple because I'm just dealing with numbers here, not expressions. So then 1/3 would equal 1/48 dy dx. And if I just multiply by a 48 on both sides, I find out that the slope of this tangent line at 864 would just be 16. So I hope this lesson on implicit differentiation has been helpful.